Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors Chapter 4 Quiz 1 Review Solutions on Exponential and Logarithmic Functions. For this example, we're trying to graph this function here using 4 points in a table. So let's make our table. Picking out the x values, we're going to use -1, 0, 1, and 2. Those are good x values to use for exponential functions because these grow pretty quickly, so you don't want to use anything too big for inputs. Let's go through and plug these in now. Plugging in -1 for the exponent, and we're going to do the exponent before multiplying by the 6 here, because we're following PEMDAS. So we've got 1/2 to the -1, which is the reciprocal of 1/2, which is 2. 6 times 2 gives us 12. Then plugging 0 in for my exponent, 1/2 to the 0 is just 1. Anything to the 0 is 1. 6 times 1 is 6. Now plugging in 1, we've got 6 times just 1/2 in that case, which is 3. And then we've also got 6 times 1/2 squared. That's going to be 6 times 1/4. 6 over 4 gives us 3/2. Now, another thing you might notice in this table is that we're multiplying by 1/2 each time. And in general, as you take one step to the right, you should just be multiplying by whatever this b value is here. All right, let's go ahead and graph these now. So we've got -1, 12. So that's 3, 6, 9, 12, just got to count these carefully, and then 0, 6, 1, 3, and then 2, 1.5, or 3/2. Now, when you're graphing this, you got to be careful because it looks like just using these 4 points that we would just keep going in this direction, but in fact, we know with exponential functions, you have a horizontal asymptote on the x-axis, so it's actually going to look something like this. For this problem, we have a cup of coffee that contains about 100 milligrams of caffeine, and they're telling us approximately 16% is metabolized and eliminated every hour. Based off of this, we want to know how much caffeine is in the body after 5 hours. So because every time increment we're applying this percentage to some original total, we've got an exponential function. So we're just going to use, and since we're not doing this every so often, since we're doing this every single hour, we're going to use our standard exponential formula. F of t equals AB to the t, where A is the starting value, B is the growth factor, and t is the time. Our starting value on this one is just going to be 100. And then for our growth factor, well, since we are losing 16% every hour, that's going to be 1 minus 16%, which is really saying 1 minus 0.16. So that's a growth factor then of 0.84. And if we were gaining 16%, then we would add 0.16, but we're losing it, so we subtract from 1. Next, we're going to plug in the time, which is 5 in this case. And now we go to the calculator. So on my calculator, I've got 100 times 0.84, and then I'll use my exponent button and exponent of 5, which comes out to approximately 41.8. And this is going to be milligrams of caffeine. For this problem, we have caffeine being metabolized in the human body at a rate of 16% per hour. Several hours after drinking an energy drink, Jane has 100 milligrams of caffeine in her body, in her bloodstream. We want to know how much caffeine was in her body 2 hours ago. So for this one, our overall setup, setting up an exponential function here, we're starting with 100 milligrams of caffeine. That's our A value. Our growth factor is going to be 0.84 because we're losing 16% every hour. And then we can write f of t equals 100 times 0.84 to the t power. This will tell us how much caffeine is in our body t hours after whatever the start time is. Now, for this particular problem, we want to know how much caffeine was in the body 2 hours ago. So we have to actually go back in time by 2 hours, which means we need negative time. So we're going to plug -2 into this function, and let's do that on the calculator now. So plugging in that -2 for the exponent, we end up with about 141.7 milligrams of caffeine. For this problem, we have a population of seagulls doubling every 13 years. If 80 are present now, how many will there be in 30 years? So for this one, because we're doubling every 13 years instead of every year, we're going to need a fractional exponent. So we're going to use the exponential form AB to the t over k to solve this one. For my A value, that's the number of seagulls I'm starting with. That's going to be 80. My b value, my growth factor, I'm doubling, so that means 2 is what we're multiplying by. And then we're going to have t over a k value of 13, because 13 is how long it takes for me to actually multiply by 2. So there's our setup. Now we just have to figure out how many seagulls we'll have in 30 years, so we'll just plug 30 in for t. And let's do that on the calculator. So plugging all that in, I end up with 396 approximately. We'll round it off to 396 because I'm not sure what 0.07 of a seagull looks like, and I don't really want to know. For this problem, we want to determine the amount of money we'll have in 8 years if we deposit $25,000 at 3.5% interest compounded annually. Since the interest is only being compounded once a year, annually, we can use the simple interest kind of setup here, which is essentially just the exponential form AB to the t, but we're going to call it PB to the t because the starting value is called the principal. So we're going to have a P value, a starting amount of 25,000. The B value, that's what we're multiplying by each time. Since we're increasing 3.5% each year, that's going to be just 1.035, and we're going to raise that to the t power now. For t, we're going to use 8 because that's how long we're leaving our money in the account. So plugging in 8, let's see what we get on the calculator. There we are on the calculator, and it looks like we're going to end up with $32,920 and approximately 23 cents if we round off to the nearest cent. For this problem, we want to determine the amount of money we'll have using the information from problem 5, which I've copied up there for us, and we're going to compound monthly now instead of annually like we did in the original problem. So we're still going to use PB to the t. The difference now is that we're going to change the b value up a little bit to account for this monthly compounding. So our b value in general is going to use this formula, 1 plus r over k to the k power. R is your rate, so that's going to be 0.035. We're expressing it as a decimal. K is the number of times we're compounding each year. So we're going to divide r by 12 because we're doing this monthly, and then all raised to the 12th power. So 1 plus 0.035 over 12 to the 12th power. And let me do that on the calculator now. So I've entered this on the calculator, and I'm also going to store this, if I can press that button there, as alpha A. You can pick whatever letter you like, but I'm going to store it as A just so that I can call up this crazy decimal anytime I want and get a perfectly accurate answer. I'm going to write the rounded off version here. So it was 1.0355, but that got rounded up, so it's got a 6. But when I actually plug this back in to my formula here, I am going to be using the value that I got on my calculator, not this rounded off version. All right, so plugging things back in, we've got 25,000, that's still the principal, times what this rounded off number represents, all raised to the t power. In this case, that's going to be 8 again, because I'm going 8 years on this compounding. So let me plug that in the calculator. Going back to my calculator, I'm going to do 25,000. Whoops, there we go. And I'm going to do alpha A to call up this decimal again. And now I just have to raise that to the 8th power to get approximately $33,064.77. For this problem, we want to figure out how much money we'll have using the information from problem 5, which I wrote up here, and compounding now continuously instead of annually. So for continuous compounding, we have to use P times e to the RT, the PERT formula, and we're going to need our principal of 25,000. The rate here is just the decimal version of the percentage, so that's going to be 0.035. And then for the time, we're going to use 8 again. So we just have to plug all that in the calculator. So we have 25,000. And to get E, I'm going to do second and then the ln button. That gives me e to a power. Second ln, there we go. And now I've got 0.035 times 8 is all going to come out to $33,078.25. On this problem, we want the log base 3 of 81, so we're essentially asking 3 to the what power equals 81, because a logarithm is just the exponent you need to raise the base to in order to get the number being plugged in. So 3 to the 4th is 81. Therefore, log base 3 of 81 equals 4. For this problem, we're trying to do log base 4 of 1 over 16. So whenever a number is a power of your base, but it's in the denominator when you have a reciprocal, you're going to need a negative exponent. So we're asking here 4 to the what power is 1 over 16? 4 to the second power would be 16, so we need 4 to the negative second power to get 1 over 16. So negative 2 then is our answer for this one. On this problem, I want the ln of the 9th root of e squared. Now ln, that's just talking about log base e, so we'll deal with that in a second. But first, to make my life a little bit easier, I'm going to rewrite this with a fractional exponent. So I'll rewrite this as ln of e to the 2 over 9. It's always power over root. And when I'm asking for the ln of this is really log base e, so I'm asking e to the what power equals e to the 2/9. And when I phrase the question like this, it's a lot easier to see what's going on here. Clearly here, x is just 2/9. For this problem, there wasn't really an example to do, but you needed to come up with logs of special cases. So one special case is when you're taking the log base something of 1. So in general, to get 1 by raising something to a power, you need to raise the something to the 0 power. And this is true as long as your base is anything bigger than 1. If you have a base of 1 or less than 1, then you're essentially asking, how do I get 1 by raising 1 to some power? And that could be any power. Or, I mean, if this was base 0, you can't get 1 out of 0. Anywho, moving on. For a less than or equal to 0, what happens if we take the log of some number in this condition, some number that's either 0 or less than 0? That's going to end up being undefined. Whenever you try to take the log of 0 or a negative number, you get undefined, because you're asking, what do I have to raise this base to, whatever it is, to get 0, which is impossible unless you're starting with 0. Or you're asking, what do I have to raise it to get some negative number, which again is impossible if you're starting with a positive base. On this problem, we're trying to do 7 to the 3 times log base 7 of 4. Now, we see the 7 here in the base of the whole thing, and the 7 in the base of the logarithm, and it's awfully tempting to just cancel those out. Before you can cancel those out, though, you need to pop this 3 in as an exponent using our pop-in rule. So we're going to write this as 7 to the log base 7 of 4 to the 3rd. And at this point, now I'm raising 7 to the thing I need to raise 7 to get 4 to the 3rd. So 7 and log base 7 cancel. I just end up with 4 to the 3rd, the thing that was inside the log, and then I'll just simplify that to 64. For this problem, I need to write this expression in terms of individual logs. So I don't want anything inside the logs except for an x, a y, or a z. So there's a few things to do on this one. We have to take care of this exponent inside. We also have to take care of the multiplication and the division of these terms. I'm going to start by just raising everything in here to the 3rd power just to make my life a little easier down the road. There are other ways to do it, but I like to take care of the exponent first. So this is x cubed, y cubed, all over z cubed. Everything just gets cubed. Next, I'm going to take care of the multiplication and the division. So when I'm multiplying stuff inside a log, I can split that up into the addition of 2 logs. And when I'm dividing stuff inside a log, I can just subtract a log of whatever's being in the divisor here. So I'm going to rewrite this as log of x cubed plus log of y cubed minus log of z cubed. So again, multiplication becomes addition of logs. Division becomes subtraction. Next, I don't want these exponents inside the logs, so I'm going to use my pop-out rule, where I'm turning the exponent into a coefficient outside the logarithm. So this is really 3 log of x plus 3 log of y minus 3 log of z. And if you wanted to, if you had popped this 3 out in the very beginning, you could have written this as 3 parentheses log x plus log y minus log z, and that also would have been technically correct here. On this problem, they want us to write this whole thing as a single logarithm, or if possible, a rational number, which we only have to do if we can actually simplify the final log. So let's start by popping in the 1/2 as an exponent on the 9. This will be log base 6 of the square root of 9 then, plus all this other stuff. Next, I'm going to turn addition of logarithms into multiplication. So this radical 9, which is really just 3, and this 24 are going to get multiplied inside one logarithm. Any logs that are being subtracted, that's going to require us to divide whatever's inside the logs. So we're going to do 3 times 24 divided by 2 inside one big log base 6, like so. All right, let's simplify this now if we can. So we've got, this will be 72 over 2, which we can reduce to 36. And then log base 6 of 36, we can actually get a number out of that. What do I have to raise 6 to get 36? Oh, I have to raise it to the second power. So this simplifies then to just 2.